Okay, so in our previous video, we talked about what precipitation reactions were. So we have what precipitation reactions are, what a precipitate is, and how to use our solubility rules in order to determine that when barium chloride and sodium sulfate combine, we do in fact get a precipitate. Now we have three different types of equations, ways to express this reaction. Our molecular equation, this is going to be kind of the full-blown deal. It's going to have full formulas, so no shortcuts. It's going to include phases. And it's going to be balanced, because we always want to work with balanced equations. So in our case here, we have our two reactants. We have barium chloride, which is aqueous, plus sodium sulfate, which is also aqueous. When we dissolve, well, water is always present. And so we have water present. We combine these two solutions. We're going to get NaCl and barium sulfate. We've already decided that NaCl is aqueous and barium sulfate is a precipitate, so it'll be solid. We have one barium and one sulfate, so one barium sulfate, but we have two sodiums and two chlorides, so we need two sodium chlorides. And this is the molecular equation. This is kind of the full-blown deal. For the ionic equation, okay, this is where you're going to split all the aqueous components into their ions. Ionic equation is representing what really is happening in solution. So barium chloride, when it's in aqueous form, okay, it's actually splitting apart into its ions. So we have barium ion, and then we'll have two chloride ions. Sodium chloride, we get two sodium ions and one sulfate ion. Then we have sodium chloride, so we get two sodium ions and two chloride ions. Then we have our barium sulfate as a solid, so it stays together, stays the same as BaSO4 solid. I don't have a reaction arrow. Oop. This was supposed to be a reaction arrow. Our ionic equation isn't super helpful for us because there's a lot going on. So what we use the ionic equation for is we use this to get our net ionic equation. And the net ionic equation is going to remove spectator ions. Now, what's a spectator ion? Well, if you think of what a spectator is at a sporting event, they are people that are watching the game go on, but they're not actually participating in the game. Okay, so for us, chemically speaking, these are going to be reactants and products that are in the exact same form. Okay, and it has to be the exact same form. Can't just be close. So if we look at our ionic equation, for example here, okay, we have two chloride ions that are aqueous in our reactants. We also have two chloride ions that are aqueous in our products. And so something that's present when we start our experiment and at the end hasn't actively participated in the experiment. Okay, so it is removed as a spectator ion. Same thing for, we have 2 sodium ions that are aqueous, 2 sodium ions that are aqueous. So these will also be removed. So our spectator ions in this case, or in this example, we have 2 sodium ions that are aqueous and 2 chloride ions that are aqueous. So now we can write our net ionic equation, okay, which is a description of what truly is the chemistry that's going on. So what is the change that's happening? And the change that's happening is where our barium ion, which is in the water, it's aqueous, and our sulfate ion, also in the water, it's aqueous. These two are meeting up in solution and crashing out. They're insoluble when they meet together, and they form this solid. So depending on what we're trying to look at, sometimes our net ionic equation is more helpful for us because it just tells us the specific chemistry of what's going on. Okay, our ionic equation helps us get to the net ionic equation. And our molecular equation tells us the entire picture. So what we're starting with chemically, barium chloride and sodium sulfate. This tells us the whole picture of what's going on. If you have my printed off notes, there's no reason why this is supposed to be capitalized. I don't know why it is, but ionic does not need to be capitalized. All right, let's go ahead and on the next page, there is an example. So will the reaction between lead 2 nitrate and sodium iodide produce a precipitate? Go ahead and try this out. Okay, so figure out if it produces a precipitate. Then also go ahead and write out the molecular equation. The ionic equation. And the net ionic equation. Go ahead and pause the video, give that a try, and then unpause for the answer. So we're looking for the reaction between our lead nitrate and our sodium iodide. So again, our positive is going to meet with a negative, negative, or positive with the other negative. So we have to figure out our ions. So we have lead is a 2+, and that's from doing the reverse charge. So the 2 on the outside of the nitrate goes up for the lead. There's only one lead, so that goes for the charge of the nitrate, NO3-. That works. Nitrate is a negative charge, so the lead has to be a 2+. Iodide, we know from the periodic table, is I-. So these two are going to form PbI2. If we look to our solubility rules on the previous page, we'll see that our halides, okay, chlorides, bromides, and iodides, these are all soluble except halides of silver, mercury 2+, and lead 2+. So we have lead 2+, so this is one of the insoluble exceptions. So that's going to be PbI2 solid. So we've actually answered our question already. Will it produce a precipitate? Yes, it will. Okay, but let's use this as an example here to give us some practice of writing these equations. So our second component, we have sodium ion, and then we have our nitrate ion. Again, remember, I'm ignoring how many of these we have. Okay, we'll figure that out once we get down here when we want to balance it. So sodium and nitrate together, they're going to have NaNO3, and these are aqueous, Anything with sodium ion is aqueous. Anything with nitrate ion is aqueous. So our molecular equation here. We have our reactants. We have PbNO3 2, that's aqueous, plus NaI, aqueous. This is going to form PbI2, it's a solid, and NaNO3, aqueous. Our ionic equation is where we're going to split apart all of our aqueous components. So we split this apart, and our sodium nitrate. So we have Pb2 plus aqueous. We're going to get 2 nitrates, aqueous. And we have a sodium ion. Oh, I'm not balanced up here. Shame on me. To balance up here, we have 2 iodides here, so we'll need a 2 out in front of sodium iodide, 2 nitrates, 2 sodiums, so we need a 2 out in front of sodium nitrate, which means we have a 2 sodium ions, aqueous, and 2 iodide ions, aqueous. I'm going to have to split my reactants and my products on 2 different lines. So our solid, our PbI2, that stays together, doesn't split apart. However, my sodium nitrate does. We get 2 sodium ions, which will both be aqueous, and 2 nitrate ions that are aqueous. To get my net ionic equation, I eliminate my spectator ions. Okay, so I see I have 2 sodium ions aqueous, 2 sodium ions aqueous, one's a reactant, one's a product. Doesn't change, so that's a spectator. Same thing here, we have 2 nitrates aqueous in our reactants, 2 nitrates aqueous in our products, so those get eliminated. So our net ionic equation is going to be Pb2 plus aqueous plus 2I minus aqueous goes to form PbI2 as a solid.